Boom! You did it, man.
We did it.
How you doing?
I'm doing good. How are you?
Pretty good. Did you do any tennis this morning?
No, not this morning.
Just chilled?
Yeah. I had an amazing sleep, though.
You had an amazing sleep?
Yeah.
I like that. That's not bad. I get okay sleep. That's not bad. Can't really say I get amazing sleep, but anyway, that's it. You ready to write some
Code?
Sudoku code?
Sure.
What happened last time?
So actually, before we switch to your machine cam, I just want to show I'm up here at github.com/kidscode1. And that's our repository. I'll stick that in the chat room there for you kids. The one we're working on today is Sudoku. There's the code right there. Recently checked in. I think as recently as not too long ago. 2 minutes ago. Right there.
Genisco 7, where are you? We need your help.
Zodu Marku, says Genisco 7.
Oh, yeah. Alright.
Mr. 7's in early.
Right now.
It's crazy, Campbell. Alright, let's go switch over to your machine. Why don't you show people what we did last time, man?
Okay. Last time
Which was yesterday.
Yes, yesterday. We made it so we added.
Why don't you run it?
Okay. Oh, yes. So we made it so that when we load the game, these values are locked, so we can't edit them.
Right. So we can load up a game, and those values can't be edited. So
Yes.
one of the things we're thinking about is like an interactive solver. That's kind of what we built in some ways.
Yeah, I would say so. And then, yes, we also we fixed a couple of bugs. There was one bug where you had to click very precisely in a square in order to get your caret in there, but now you can click pretty much anywhere in the square,
Right.
and it will.
We did. What else?
We also fixed a bug where, I'm forgetting what the bug was.
I don't remember any other bugs, but I do remember a feature we added.
Oh yeah, a feature. What was the feature?
I will give you a hint, and it'll be the color. It's red.
Oh, so when there's an error, like if we try to type in a 4 here, it will highlight all the errors.
Yeah.
And it works in the block, row, and also column.
Yeah.
Wait. Dang it.
So if you did this, here, let me show you.
I'm looking
Can I give you a
one.
demo? Here's a great demo.
Oh, wait,
you put
wait.
an 8 here. Whoops.
Wait, so if you put an 8
Wait,
here,
wait.
it will show.
There you go. You found it.
Yeah, in the row, the block, or the column.
Nice demo. Good job.
I was looking for one of those.
I was too. I didn't see that.
Mm.
So it highlights all the problems.
Yes.
Row, column,
And
block. Okay?
Yeah.
That's what we did. Today we're going to implement what we're calling Advanced Solving Logic.
So right now our current logic is we show the notes, so every possible number, and everywhere that there is only one possible number, we just fill it in there. So if we hit solve again, we'll see, a 5 here, a 4 here, a 3
Wait.
here.
Before you do anything, watch this. See the 6 here? Oops, sorry. See the 6 right down there?
Yeah.
When that gets filled in, it's going to take all the 6s away from here and here
Yes.
and here, which means that'll become a 1 after you hit solve. So hit solve and keep your eyes down there.
Yeah.
Go ahead and do that.
And then,
Sorry, my mouse is
Yeah.
getting me right.
And then, so this is now a 1, so next time this will become a 1.
Yeah, and that
And also-
3 on the left will become a 3.
Yes, and this 7, it had a 6 as well. And so now when it becomes a 7, this one will become an 8.
Right. We're just kind of incrementally
Process
finding
it
our way
within
through.
a little
So it's not a bad way to solve the puzzle, but
it doesn't work for everything. We have a game that is hard. So this one we still can't solve. We get to a certain point when
that's it right there, right? We've got a bunch of pairs. See those 3 4s?
4, 3, 4.
Got some pairs in there.
5, 7, 5, 7, 5, 7 as well. Yeah.
So we're going to use another technique to solve them.
Even this one, 4, 5, 4, 5, 7, 4, 5, 7. Which doesn't really help because this row is pretty much filled in.
Yeah.
For all of these.
Now, notice if we're looking at this one down here, we have a 4, 5, a 4, 5, 7, and a 4, 5, 7. We know that the 4, 5, and the 7 are in these three. We know the 7 has to be in one of these two. It has to be because I need a 4 or 5 here, right? So if that's the case, then we know the 7. When you take the 7 away from here, 7 away from there, look, leaving only 5 and 8. We're cleaning that up, right?
Yeah.
Take the 7 off of there as well. So there's a more advanced solving strategies. And so we're going to kind of implement those today. We're going to look at that and implement those. We talked about these a bit yesterday. I'll switch over to my machine. One of them is, hey, look, if I've got two identical sets of, if I have two squares in a group.
Which we have. Can we switch over to my machine real quickly?
Uh-huh.
Yeah, we have here. We have 3, 4, and 3, 4, which is a great example of it.
Right. Yeah, and if that's the case, so what's cool about this is that we know either the 3 or 4 are essentially in those two spaces, or basically here a 1 or a 2 or a 1 or 2.
Yeah.
If that's the case, then we know if I have these two, then every other place in the row that this is in, or the group that these two are in, they cannot have the numbers 1 or 2 in them. We can remove those from them. That's kind of what we can do. So let's work on that. I think what I want to do is we'll work on your machine.
Okay.
I think for a little bit. And I want to do a couple things on this. I want to go over to Sudoku Square. And this is kind of what I would call a heavy class. It descends from user control, which means it's got a lot of properties in it. If we look at this while we're debugging, there's a whole bunch inside of this.
Yeah.
We see like 100 properties.
Yes.
I want to do this. I want to use a coder's feature called extract interface on this. And we're going to learn about interfaces now. And what extract interface does is it grabs all the public pieces from it and pulls it out. Industry 7 says when two options for two fields in a square, there can be another square with the same thing. I think that's true, based on what I understand you to be saying. All right, so what I've done is I've extracted this interface out of Campbell, and this interface basically has all the public methods. It already contains the definition for Sudoku square. Where? I don't see it. Let's build it and see what the problem is.
Wait. I think I know what happened. So, let me just...
I'm just going to do a find for everything.
Okay.
I guess to say yes. Oh my gosh, it's going to get really, really hard. I'm just going to save for a second. And let's go again, make sure we have, yep, the stuff that we have it already contains it. So I'm going to search for this, find out where it exists.
I think that what I did is, it was in rename mode and I accidentally got rid of the I.
Oh, so, did you rename the other one?
Yeah, and then I undid it. And so I think what happened is...
That one looks right. Ooh, that's my problem.
Yes.
Okay, there, it just changed back though. Did you change it or did...
I didn't change it. Here,
That was
wait.
weird, I just opened it up. Close it.
Yeah,
Let me take the mouse a second here. I want to try to rebuild on it now. Is that our problem? That interface is correctly named. Ooh, there's my problem right there. Okay, I see. I think I see what happened. So it's probably a rename, and yeah, what you ended up doing is renaming Sudoku squared to it, is what you ended up doing. The cool thing is we checked everything in before we started, and pretty sure we can just take all of this and what's remove do? Remove's not clear to me. What is it doing? Contain changes in information which is not source control will be irretrievably lost if you remove them. I think that's what I want to do. I'm just not sure if it's confirm remove modified or untracked files. I don't necessarily want to remove them. I want to ignore the changes. I want to discard them. But there's no option to discard here. So what am I going to do? I guess I'm going to do this. I'm not sure. I'm going to take this, do a search and replace that to that. Do that. Now, try to rebuild it. That looks better. Still got our iSudoku square out there. All right, cool. That wasn't too hard. Okay, so thanks for pointing that out, Camel. I was like, it added some explanation. So now I've got this interface, and the interface, the thing about the interface is it's lighter weight. It's like a contract. It's like something that says, hey, you can depend on me to be able to always do these things.
Yeah.
Okay, and now if I want to, it's lighter weight. In fact, what I can do is I can make it even lighter weight than this and say, well, you know what, maybe I really only want its char and its notes. For example, I don't care when the value is changed. I just want to know about its char and its notes.
Yes. Wait. But we want to know also about all of the other things that it does.
Like what?
Like value changed.
Not if I want to deal with it on a low level, and I want to kind of make it lower level when I'm thinking about problem solving. When I'm solving the problem, when I'm solving the problem of implementing the logic, I want to deal with something simple. So I'm going to do this. I'm going to start with this one, Camel, right here. So char is basically, that's what it's filled with, the value it has. I wonder if we should rename this to value. Like that. I just renamed it. Why didn't it rename it over in, oh, because we're not implementing it. Okay, hold on a second. Let me undo this. Undo this. We need to implement this. We lost a piece when we undid, I think. Let me come over here. So I'm going to put a comma here and I'm going to add iSudoku square. So now that means this is implementing this contract. It's agreeing to the contract. It says, I will do that thing that you say.
Okay.
This allows me to have this big...
So now you can use all of the things that iSudoku square does in this method.
Well, yeah, and I can pass the Sudoku square to it, but the thing that deals with it doesn't need to know about everything else. So it doesn't have to have all these dependencies on the UI, the user controls. It doesn't have to know about focus. It doesn't have to bring in all those assemblies in. So it allows us to create a small dedicated feature.
Okay.
Okay, that's what it allows us to do. That's kind of what we want to do. We want to look. We're thinking lightweight. This has advantages as our application gets complex to be able to think lightweight. Okay, as our application gets complex, being able to think and use lightweight pieces is way better than heavy, expensive pieces.
Yeah.
Okay, because then I can do testing, for example, on lightweight pieces. So that's what I want to do. I want to get an iSudoku square that just has this. Now I want to try and rename, and watch this. When I rename this to value, and then hit enter and tap next reference, look what happened. It changed this one in the contract. Because we said, hey, Sudoku square implements iSudoku square, sorry, because it implements that, and then we renamed this, it also renamed its char to value.
Oh, okay.
And then also renamed it here, okay? Because it's now the iSudoku square.
Yeah.
Sudoku square. Okay, next, I need a class that can analyze 9 of these. right? If we look over here in my
81
machine,
of them.
a row, a block, or a column consists of 9.
And we're going to be using that 9 times. No, wait. More than 9 times. We're going to be using that.
Well, I don't know how many times we'll use it, but I do know that we need a class to solve it. So I'm going to call this the
27.
group solver. Maybe I'll call it base group solver. And I'm going to create some descendants of this class. Do you know about this inheritance? Have we talked about that at all?
Yeah, I think we have.
Well, just in case. Time to make some.
Cool.
We'll talk about inheritance. Inheritance. And maybe also and implementation.
Yes, I think we have talked about inheritance.
I'm going to call inheritance one thing, and I'm going to create another slide. We call it implementation. Apologies for that, they both start with the letter I. Because it may make them for a moment, hard to differentiate.
But it also makes them easier to remember.
Hopefully.
Since it's a...
Agrees to a contract. The contract is defined in an interface. Example? Well, it's from your machine. I'll just copy this and bring it over to mine. Here's the example. Like that. That's an example of an interface. And these are just methods or properties. These two are properties, but you could also have methods in here.
Yes.
So this is the type of the method, or the type of property rather. It's a value. Does this have a setter? Can I set this value at all?
No.
It's only got a getter.
And then the next one after that has a setter. So
It has setter, right. So I can set the notes and I can get the notes. Okay? That's an example of an interface. That's an example of an interface. Okay?
yes.
We learned interfaces and implementation. We're going to learn inheritance takes us 3 I's, Campbell.
And it's an alliteration, so 4.
It's an iteration? Well, I don't know.
Alliteration.
Oh,
Alliteration.
alliteration. Does that begin with an A?
I thought it was with an I. I can
Alliteration. I think it's A. Okay, there's an example of interface. All right, cool. So, the benefits, let's get down here and talk about benefits of this. We talked about them a little bit, but
Oh no, you're right. It's illiterate is with an I.
Sure.
But
Okay, hold on a second.
alliteration is with
I want to get that guy back up there again. Okay, so example, and then what do I want to say? Oh, benefits. Benefits. Well, it's lightweight. It can be simple. It helps you simplifies complex things into smaller pieces. Right? So, and it reduces the otherwise heavy dependencies that would be needed if we worked with a heavier class. Okay?
Okay.
So it's basically implementation and interfaces of interfaces, maybe a better way of saying it. Interfaces, I want you to think lightweight. Okay? That's the benefit. Inheritance. This is when a class can do what its parent does.
Yeah. Like in Unity, all of the classes were children of monobehavior.
We're what?
All of the classes
We're
in
descendants.
Unity, descendants of monobehavior. I was getting child statements confused with.
No worries, it's all new, right? We're descendants of mono behavior. We saw that.
Yes.
And it's when a class can do what its parent does, right? So that means we can do what the parent could do. We can also call methods that can be implemented by anyone in the ancestry. For example, start and fixed update. Right?
Yes.
We can call those methods, right? So we can look for those methods and call them. This is kind of maybe not the best example as I'm now thinking about it, because this is using a different technique the way Unity does this, but conceptually it's identical.
Yes.
Maybe I'll just write this down here. Conceptually identical to Unity calling start, calling these methods in our script. Like that. So visually, inheritance, oops, I didn't want to do section. I wanted a new slide. Visually, inheritance looks like this. Got some sort of base class here. And from that, we descend a child. Like that. It's kind of like that, is what it looks like. We can, sometimes we turn this arrow around. We put this one going here, so indicating that this inherits from that. Like in a class diagram, you might see that. So the arrow points up. But essentially, the guy up on top, this guy, that's the ancestor.
Yeah.
And the guy down here is the child. Okay?
Yes.
So that's kind of what we're talking about right there. Cool. And so that's what it looks like visually. So in code, it looks like this. Let's go back over to your machine. So in code, I create one class, and I'm going to add the word base in it, indicating it's an ancestor. And then what do we want to do? We want to be able to we want one method in it called solve. I think it's going to take in an array of Sudoku squares. Okay? So there'll be an array of those in there, and we're going to call this the group. And I'm going to make this, I think, abstract. Abstract means I'm not going to implement it here.
Huh. Why are we using abstract?
And I'm going to make this class abstract as well.
Where are we going to implement it then?
Sorry?
When are we going to implement that? When are we going to implement it?
That's a great question. Where are we going to implement it? Well, I'm not going to do it here, but watch what I'm going to do next. I'm going to create a new class called Solver 2x2. And I'm going to put the colon right here, just like we saw with mono behavior.
Yeah.
And have it descend from base group solver. Then I'm going to hit the code brush key here. I'm going to choose implement abstract class. And it's going to, look at what it did, added this method.
Oh.
Using override, which overrides this.
Okay.
Okay? So I can declare abstract methods up in my ancestor class. And in my descendant, I can override them and implement them. Okay?
Yes.
Cool so far? Now, my base group solver, let me show you what this is useful for. I'm going to come over here, and somewhere in my initialization, here it is right here in my main menu. Here, the main window. Let's do this. Let's first take all of this. Take all that, let's extract that to its own method. Because we didn't have a lot of symmetry here. We got this cool initialize component method, then we have this cool hook events method, but then we got all of that other stuff.
Yeah.
It's not symmetric. So what I want to do to make it symmetric is extract it to its own method. And now here, I'm going to call this initialize squares. Like that. And I'm going to call another method called initialize solvers.
Which hasn't been declared yet.
I'm going to declare it. Fine, I'll put it here. And now what we want to do, well, let's see. I want to say, I want to create a field variable that holds all my solvers. So I'm going to come up here, and I've got, notice base group solvers on the clipboard. Go ahead and type this in for me. I want to create a new list of these. So type in nl dot, and then the slash for what's on the clipboard. It's the backslash, the one that's above the enter key. There you go.
Yes. And then space?
Yeah. And then call this solvers. Notice these are a list of the base group solver. They're not a list of the specific ones.
Solvers?
Yeah. Copy that to the clipboard. Hit Control C so we got that to the clipboard.
C.
Hit Escape to get back to the marker that I should have dropped down below, I hope. There it is, cool. Now what we want to do is we want to say solvers.add, and then I'm going to add a new solver 2x2 to it.
Ah.
See? Later I'm going to add a 3x3 once we get it. That rule done. That's a harder rule to do.
Okay.
Okay, but I'm not doing that yet. So now we got the solvers in here. Now we got to solve it. So somewhere in here, we have to figure out where we're going to solve it. Fill from all notes is when we click the solve button. Then we've got to refresh all notes, which does show notes for square. But we don't have anything that says solve.
We don't.
So I'm just trying to figure out, I don't know where we're going to do this yet, but we need to either add a button to apply this logic, or we need to call it like somewhere around this point, maybe after calling refresh all notes. That's kind of what I'm feeling like. So for each solver, call it Sudoku.
Sudoku.
I've got to stop transposing. For each Sudoku solver and solvers do, and it's got this solve method that takes in a group of iSudoku squares.
Oh. Okay.
All right, and what I need to do.
I think you need to give it some parameters. I think because error.
Yeah. I think I need to pass in, I need to do a couple things here. I need to say, I need to pass in 9 rows, 9 columns, and 9 groups.
Uh-huh.
Let's look at the picture of it. So you see what I'm talking about. I got to pass in this column, this column, this column, 9 columns. See that?
Yeah.
Because each one of those is, I got to do the rules on each of those columns. I got to pass in 9 rows. See it?
Yeah.
And then I got to pass in 9 blocks. 1, 2, 3,
Yes.
4, 5, 6, 7, 8, 9.
So it's 27, right? We use it 27 times.
That sounds right. Okay? So, that's what I need to do. So, then what that means is I need some code that looks like this. So, I'm going to do this, and then I'm going to do solve, and I'm going to call get column.
Yeah, I think that's get column.
Pass in C.
And then get row for the next one.
Get row. There.
Yeah. And then get block for the next one. But get block is different, if I remember correctly.
Yeah, get block is trickier. It is trickier because we have to figure out, it's not really so much an R. I guess we could do this. I think it looks like this. But now what we're doing is we're going to go R is less than 3 and C is less than 3. Then we're going to say get block, and he needs a row and a column. I'm going to say R times 3 and C times 3. And I think that'll get this combination will get every block. So if it's not clear what's happening, I'm going from row 0 to row 3 and from column 0 to column, to column 2 and to row 2. So I go 0, 1, and 2. Those numbers iterate from 0, 1, and 2.
Yeah.
But then I multiply those by 3. So that's going to give me 0. 0 times 3 is 0.
0.
1 times 3 is 3.
3 and
2
6.
times 3 is 6. 0, 3, and 6. That will give me those blocks that I need from each of those places.
Yes.
I'm pretty sure that will work. Okay? So that's how we're going to call it. And now the question is, do we call refresh all notes one more time? And I think we do.
Really?
That's
I don't
what I
think we
think.
need to, but
Show notes for square, what's it do? It's row, column, yeah, it figures out the values. I think we're going to need to call it one
Okay.
more time. So refresh all notes the first time gets them based on what we know. That can make sure our notes are valid. But now after we potentially solved, we're going to do it one more time. So we do one more thing on this. Our solve function, instead of returning a void, could return a value, like an enum, like solve result. None, and
why would
elements change. What are you thinking?
why do we need it to return a value?
Oh, because then we're back over here, right? If anything changed, we can refresh all notes, but if nothing changed, then we don't. We need to know, did we solve anything or not?
Oh, okay.
So that's kind of what I'm thinking. I'm thinking, okay, so let's have this return a solve result instead,
Okay.
right? Which means this has to return a solve result as well, okay? And so now, if that's the case, that means I can come in here and I can create a Boolean right here that says changes made, something like that. Or squares solved is probably a much better name for this. Squares solved, set that equal to false. But then here, do this. Hey, if that is equal to solve result.elements changed, then I'm going to set this to what value? What does that set to?
Is equal to none, right? Or elements change? No, elements changed.
It's a Boolean. See it?
Oh,
You can only do one or two things, true or false.
then it's equal to true, right?
Okay? And that's kind of how I do it. So we'll do that there with R, and then do this similarly here. Where we say, hey, if we do this, that is equal to solve result.elements changed, or solve, we may rename that to solve. We're going to choose square solved is equal to true. And then down here, finally, so the question is, why do we do all this? Then we'll only refresh the notes one more time, go through them all one more time if anything changed. Okay? Let's rename this. Square solved. Okay? Are you good with that?
Yeah.
Okay. So we've got this solve method now. We're calling it 27 times. All the rows, columns, and blocks. What's 3 to the third power?
3 to the third power is... Wait, 3 to the third power is... It's 27, right?
It is 27.
Yeah.
If we were dealing in 4 dimensions and we had a 4 by 4, we would now be 4 to the fourth power in this step right here.
Yeah.
We would have to do all the columns, all the rows, all the blocks, and all the whatever the other
Whatever
fourth
it is.
dimension is. Yeah.
But right now, we're
Yeah.
not really dealing in the third dimension because we're dealing with blocks, not...
Right.
Really?
It's arranged in 2 dimensions, but
But it also has the
Yeah,
blocks. So it
there's
is...
a little bit.
It's
Yeah.
3-dimensional, but not like our 3-dimensional.
It's
Not
kind
the
of it's
3-dimensional.
definitely a hybrid, I would say. It's kind of it feels like a hybrid at least. I'll say that.
Yeah.
Okay, now we gotta actually solve. We gotta do something in here. So here's our first solver. This is our solver 2x2. I'm gonna move these to separate classes. Like this. Move this one, the base group solver. Like that. So again, there's our ancestor class. I'm not going to implement this here. Can you see that? It says abstract right there. Got that?
Yeah. Got it.
Okay. Now we got everything in there. Let's just run it. There should be no change at all in behavior. Just make sure it still works. Because we're not solving, we're not doing anything. Go ahead, interact with it. Verify that everything that we know to be true about this still seems to be true. Ooh,
Forgot to do that.
I'm going to, instead of do this, I'm going to return. I'm going to go ahead and do that. By the way, look at what Coder says for me. Right here, hit R space. Right here. Remember R does the return template? Look at suggesting solve result.none. That's exactly what I want. Just hit enter. And now you can run it. Hit run on it. It should work.
Uh-oh. No. Wi-Fi is going... Oh, wait, no. Oops.
Step 5. Hit continue.
Okay.
Alright. So
Everything
now go ahead
froze
and
for a second.
verify it all still works.
Okay. Wait.
At least the same behavior we saw before. Right.
Everything seems to be the same, and now I'm
Okay.
gonna try it with the hard one as well.
Okay.
Wait. Yeah, okay.
We added a third game in there as well. That was a medium
Oh, yes.
game.
Medium
Try that.
game. Control Shift.
You haven't seen it actually work with this. Yeah.
Oh,
The medium game, yeah, it doesn't look like there's a lot on there. That looks like a hard game to me. They said that was a medium game. It could only do one step.
I don't think it couldn't even do one step. Look, if I wait, Control Shift load game, and then I hit solve, it only shows the notes.
And that's it.
Yeah, nothing.
Keep hitting it, nothing happens.
Yeah.
Don't forget to tell me I'm hitting it because we can
Yes.
hear the click.
Sorry.
Yeah. Okay. Yeah. So that
That
other
might
game
not
was
have
hard
been-
too.
Sorry. I should probably change that.
Change what?
Change that medium game because it's harder than our
I
hard
don't
game.
worry about it. Well, we won't worry about it for now. All right. So now we got to figure out how to solve. We're going to get a group of squares in. Right. We need to solve it. Now we were talking about how to solve this earlier in the show. Switch over to my machine here. Basically, we want to go through the 9 squares. Let me just duplicate this a second. And let me just get rid of all of this red. Boy, is that hard to look at. Like that. So what I want to do is I want to go through all of these. Let me put my steps over here. Step 1, or I don't know. I'm going to say iterate. Check all of these. Check all squares. I want to add the notes to a dictionary. We were talking about this earlier today before the show. Do you remember this, Campbell?
Yeah.
A dictionary of, well, indexed by the notes, by the note text,
Yeah.
of a list of
The indexes. So
the
where
indexes into the group. And what that means is, if this is the first one in the group, this is the second. In fact, really, it's probably not a good idea to have them in a line like this because it implies it's two-dimensional. What we're really talking about, did I not get these because they're grouped there, I see. what we're really talking about is 9 of these. We'll just put these over here. Pop these out on the end. Get all of these, group them, and now resize them so they fit on screen. There we go.
And then also, yeah.
So I say index to the group, so we'll put our indexes up here at the top here. So index, this is it's a one-dimensional array. So the index into the group is up here at the top. I'm going to change the color of this, so we're going to use color coding to indicate, maybe red. It's going to be my index. So there's my index, and that means that this one is at index 0. Like that, right there. This next one's at 1. Right, 2, you get the idea.
Yeah, yes.
All the way
So
out
on
to
and
what's
so
this
forth.
last index?
8.
Right, it's 8. Okay, so that's all the way to there. So I've got 0, 1, 2. Those are my indexes. And so indexes into the group, I am going to make this color coded as well so that we can see indexes are red. Okay, and indexed by the note text, let's make the note text blue. Is that cool with you?
Yeah.
So we'll make it blue. And that means we're going to change this text as well to blue, like that. Then I'm going to change let me ungroup this a second, because I just want to grab these pieces here. And I want to change the outline to gray, so you don't have color here. Okay?
Okay.
All right. So that's what I want to do. We add the note text to the dictionary, index by note text, and a list of indices into the group. So the dictionary, if we find something, we're going to add it to the dictionary. And if it's already in the dictionary, we're just going to add what we find, its index, into the list. What's cool, these are, by the way, ints, Campbell, these indexes, right? They're just ints, right? What's cool about this is at the end of the process, when we're done, the dictionary lists will tell us how many we found, matching that we found. Then we're going to go through those matching. Hold on a second, let me get this, move this down. And then we're going to basically say the rules on the matching are, actually I want to bring this into a separate box here, over here. So what we're looking for is we're looking for 2 numbers long in 2 cells,
Ah.
right?
Yeah.
And only those 2 numbers in only 2 cells. We're basically looking for a dictionary entry holding, which is a list, right? Holding a list of exactly 2 elements. That's what we're looking for. So we're looking for that kind of thing. And that will help us find the 1, 2, or whatever the matching. Once we find those, then we'll go to the next step. But let's see if we can find those first. So we need to check all the squares, add the notes, collect the notes in a dictionary. So back over to your machine. What we need to do here is we need to create a dictionary. And I think we can probably do it right in here, locally. So I want a new dictionary of string indexed. I can't do a secondary piece here. I'm just going to call this I for now. And then I'm going to replace I with a list of ints right there, like that. Okay? Like
Okay.
that. And then, so this is going to be my dictionary. Then I'm going to go through my group. So I want a for loop here. 0 to, and look at that, I can use group length like that as well. So I didn't have to specify 9, which is cool. And now I want to say this. I want to say, hey, if group of I, so that's one of these, dot notes, that's what I'm looking for. It's not really this, it's really the dictionary. If the dictionary, we're going to call contains key on it. Does it have the key already? And that's great news.
If it does, then
Yeah. Let's say it doesn't though. Let's actually put a not here instead. If it doesn't, we're going to come in and say dictionary.add. We're passing in our key, which are the notes, right? And then we're going to pass in a new list of int to it, like that. Okay? We're just initializing it, right? But now that we've done that, now that the dictionary has it, let's do one other thing to make this simple. See how this is showing up a couple times in here? I'm going to come down and do introduce local for all occurrences, and we're just going to call it notes, like that. So it's a little easier. See?
To read.
So now we're going to add notes, and then now that it's added, on the next line, I can say dictionary of notes dot add, because this is a list now, and I can add my index to it. So the first time we go in and find it, the first time we find something, it won't contain it. So we'll add a new list. And then we'll immediately add that first I to it and in its list. The second time we find it, we'll be like, cool, we'll just skip right past this, and we already got the key. And then we're going to add another element to that list. So it'll be like index 0 and index 1. And then we're done with that first pass. So that's our first pass right there. That is our first piece. In fact, I might even come in and work on that. I might extract that in a second. Now what we want to do is we want to go through all of our keys like that. So we'll just take that, cut that to the clipboard and type in FE for each, like that. And Coders will expand that template for me, right? So now I'm going to go through every key in the dictionary, right? Those are all my notes, right? And I'm going to say, hey, if dictionary of key dot length, no, dot count, its count equals 2, like that. And, well, let's just start with that. And I'm going to say, I'm going to put a comment in here that says, hey, this is magic. That's what we want. We're looking for that. But before I do that, I want to do one other thing. The notes that we track, these notes here, because it's a 2x2 solver, Campbell, is it useful if there are 3 entries in the notes?
I don't think so.
Well, let's look at our rule.
Oh,
Does my
right,
rule
yes,
have any,
because we
is,
have
is my rule
the
going to be able to
column.
work if I've got 3 here? If
Oh,
I have
no,
one,
no,
two,
no,
or 4?
no.
It won't work. It only is going to work. This rule
When we
only
have
works
2.
if I have 2. Okay? So I need to have 2. If I have 2, how many commas are inside?
1.
Right. I think there's a string function that can count commas, and all I have to do is just look to see how many commas are in it. And so what I want to do is here, is I want to, once I get the notes back over to your machine, right here, I want to say, hey, if, is there a get count or something like that? Notes.count. What's this? It shows the number of elements in the sequence. And it takes a function and a predicate. Interesting. X equals comma, like that. If counts of that is not equal to 1, then I don't want to go into my logic. I just want to do a continue. Did I not do something right? Yeah, that is right. Okay, good. So I'm just checking to see, must have at least, must have only 2 elements for this to be interesting, for this rule to work. Okay? Does that line of code make sense to you? Notes.count, it takes a predicate, which means I'm going to, for every x, I'm going to check to see if x is equal to a comma. And if it is, it's basically, that's how I count my commas. Okay? Another way of doing this is here, let's do this. If that's not easy to read, let's extract it and call it comma count. Like that.
Okay.
Better?
Yeah.
If comma count is not equal to 1. So a 1 means 2 elements. Does that make sense? Or I can maybe even do it better than this And I could say, let's rename this to note count, and let's return a +1 on this. So note count, and now look at what happens if note count is not equal to 2. Look at that. Code gets way better. I don't need to comment anymore. See it?
Okay.
Note count, note. All right. I think that's going to work. So now we're going to check to see if the dictionary count as well. So we have to have 2 notes in 2 entries that match. At this point, we have magic. Okay? And what that means is that we can remove, what does it mean, Campbell?
We can remove whatever those 2 numbers are from every block they're in and every row they're both in.
Right,
or
exactly.
if they're both in the same column,
Yeah.
we can do that.
Yeah. So now we've got dictionary key. This is the list of the indices that we know these 2 values are in. That means every other one in this list does not have them. So what that means we can do now, this is really like high level right here, but we want to go through the group again, is what we want to do. We want to go through the group, and we want to check to see if this index into the group is not equal to one of those indexes in this. So this, remember, right here, in fact, here, let's make this easier to read. Let's take this and introduce a local for this. And we're going to call this list. Okay? It's just our list of ints. So if the list count is 2, great. Then we're going to come in here and we're going to say, hey, if list.contains I, so we're going through the list of indices. If my list contains it, then we're going to continue. Okay? But now, if it doesn't, that means we're in a really powerful place. So right here now I'm going to move my this is magic. This is magic. This is an element that is not in the group. That is not in the squares, the matching squares we found. And so we can remove the notes.
Yes.
The notes from here. Okay, so now what we have is, so that means we probably should call a method here, remove notes from group of I, that's the Sudoku square, okay?
Yes.
And the piece we're going to remove from, hold on, my brain is about ready to give out. Let's look at this carefully. It is, I think it's fair to say it is group of list of 0. Holy cow, is that mind blowing. List of 0 is the first element. These are both, oh wait, it's key. It's easier to just get to key. We'll do key. Key is going to be 1, 2.
Okay.
Okay, remove notes from group. Let's declare that. This is going to be, we'll call this notes, Sudoku square, and here I'm going to set a breakpoint. We're not going to do anything yet until we get in here. See if we actually get here, right? I think we should set a breakpoint here and solve, right? Because there's a lot of code. Okay, and it was mind-numbing code. If I'm over here, Campbell, trying to hold all this together, you must be over there like, what's going on? Dad, I didn't sign up for this. I just want to be a boy and hang out and play ball. Jump on the trampoline. All right, so let's load the game up. Let's load the
hard game?
Yeah, it's
But
solved.
not the super hard game.
Yeah. Okay, look, we're in. Let's hit F10 and step through and see what happens. So we create our dictionary.
And then we go through this.
Every element in the group. Hover over the group. How many elements are in that group coming in?
Let's see. 8.
9.
Or no, sorry, 9. If you
Right.
include.
excuse me, nine elements are in the group. So we're going to go through every square in the group.
9 times. Or we're going to go through it 9 times.
Yeah, hit up 10. See what the first note is.
No.
Well, it's,
Or wait, that's a group.
it's null over on the right. That's interesting. Hold on a second. I wasn't expecting null to come in for notes. Let's look at the call stack.
Wait, I think it's null because we already have something in there.
The first all notes should have put them in there. That's really interesting. Hold on.
I think it's because we already have something in that square that we're looking for notes in.
Oh, okay. That could make sense. All right, so let's jump, take a look at this. Let's see what happens with node count. I'm going to take over in a second.
Yeah.
I think it's going to be problematic because nodes is null. Look out, man.
Oh,
Pudding's
hello,
here.
pudding.
I love it when pudding shows up. Always nice to have a break right here. Okay, I gotta just do a check in here. Node count. So I'm gonna basically say, hey, if this is null, then return 0. I'm gonna bring the execution up here, and we're out. So we continue. What's interesting is if we get past to here, I want a breakpoint there. I'm gonna hit run. We're back in again. So we didn't find any in that last group. Let's hit run again.
Okay.
Oh, we didn't get any at all? Okay, so we got a problem. Are notes always null? Let's go see. This is the implementation of notes. Notes is always null. We added a string here, Campbell, but we never populated it with anything. I was depending upon and using this, but we're not doing anything with it. So let's make it work. I'm going to stop the program a second, and look, we're going to make notes work. So to do that, I'm going to come down here in the get. I'm going to give it a set of braces. I'm going to do the same thing with the set. I'm going to give it a set of braces. Remember, this is a property, so these setters and getters are accessed. We do have something on here called what? TBX notes? No TB notes? There it is right there. So I'm going to say here on the get, I'm going to say return TBX notes dot. Is there a text property? There it is. Sweet. And on the setter, I'm going to say this is equal to value. Okay? All I'm doing is I'm using my control on the form, my text block, as storage for this.
Okay.
Okay? Let's run it again and see if we get a different, result. Hit start. How you doing, Pudding? Pudding says, hello, Campbell Murky. How are you guys doing today?
We're
Hope you
doing
got a nice
pretty good.
breakfast. I did.
Oh, I had a great breakfast. I
Alright.
had avocado toast.
Avocado toast. Campbell made his own guacamole this morning. The kid takes care of himself. All right. Dictionary contains key. Look, we actually got 2 notes now. Hover over notes, the string. 5 and 9.
5 and 9.
Sweet. So now we're going to add it. So hit F10 to go down to the next line to add.
F10.
Now we're creating a new list in the dictionary. Okay, and it's indexed by the key 5, 9. Okay, hit F10 and then hit F10 again. Now we're adding 7, which is the index of this. 7 means we're almost done. We're almost all the way through. I don't know if we're going to get another one because we only got index 8 to look at. Right? So try to see what we get there. 4 and 5, it's not 2, but it's also not 5 and 9. See?
Yeah.
So what's going to happen? Well, we're going to add it. We've got a new key in there. And keep hitting F10.
Oh, it changed.
It's in a different key though. And then now keep going, F10. So we know that this collection appears to be working now. Keep hitting F10, you're about to end it. You ended that loop and you're into the new one.
Yes.
Hold on, let's turn off this breakpoint. We're now in the second phase. So phase 1 we've gotten through, now we're here.
Wait, there's another breakpoint we need to get rid of.
If we hit it, we'll just clear it when we hit it. So now we have 2 keys in the dictionary. The problem is that each of those keys, the elements for it is a list of only 1 entry on it. I'm not sure we can get in there and actually see. Here we go. See the count? 1 and 1? That's not what we want. We're looking for a 2 somewhere in there. So we didn't find it. We'll never get in here. This is our breakpoint of interest. We want to be able to get past this line of code. See it? We count as 2.
Yeah.
Hit run and see if we get in here. It would be so sweet if we hit that. Ah! We can't. We don't hit it. Our rule doesn't work anyway. Oh, wait.
We do. We just have to hit solve.
Oh, okay, cool. Sweet. Nice. So check this out now. Now what do we have here? Let's see. Let's go ahead and hit F10 and let's watch what happens with the code.
F10?
So now we're going to go through every element in the group. And we're going to check to see if it does not contain this. And so we're basically looking at, we expect it to go through 7 elements in the group. 7.
Yes.
That we do and 2 we ignore. Okay, go. Hold on. So now we're taking in a square at index I and 5 and 7. Hit F11 to go inside this one. Ah, and now we're not doing anything. So now we want to remove it from it. So let's go look at the Sudoku square here. And Sudoku square, we're going to say, hey, if Sudoku square dot notes, let's see what that is. I'm just going to hover over that. It's empty. Okay.
Oh, I think it's with.
That means it's solved, right?
I think it's with a lowercase n.
No, it's showing me a value, so there's something there.
Oh, okay.
So there's no notes in that one there. So I guess we just do this. You can say, hey, if this is null or empty, then return like that. And we're really looking for. Maybe I'll do an else begin right here. We really want to break point here now. We're looking for something there. Let's keep hitting run until we get it. Cool. Now we've got, oh look, 2, 5, and 7. See it?
Yeah.
And we've got 5 and 7 here. With me?
Yes.
We need to remove this 5 and 7 from that. So what we need to do, but we need to find them. We kind of need to convert it to a list of numbers, pull the numbers out. We need to convert both of these to a list of numbers.
Yeah.
So what I'm going to say, we'll call this to remove list. And this is going to be a list of ints. Whoops. Like that is equal to get numbers. And we're going to pass in the notes. Like that. And then we're going to create a second one that's going to be to this is going to be the square notes, maybe? Like that. Like that. And then I'm going to say, I want to go through each one of these. For each number to remove, in to remove list, we're going to say square notes dot remove, and we're going to pass in that number, the number to remove from it. And then at the end of this process, we're going to say Sudoku square.notes is equal to, we're going to call a method called join. And join is going to take a parameter which is a separator, which is going to be comma separator, and it's going to take an array of values, which are going to be my remaining square notes that exist here. Like that. And that's going to put them back in. Okay?
Okay.
We just need now to declare get numbers. And get numbers, we're going to come in here and say we want to have a new list of ints, like that. And we're going to say call it result. Like that. And then we're going to come in here and we're going to say notes.split. Remember we saw split before? You were like, I'm not sure what split does. Like
Yeah.
that. You remember what it does now?
No, I don't remember.
All right, well, let's step through it and we'll see what it does. And then at the very end, we're going to return result. Like that. I'm going to set a breakpoint in here. And let's keep going. Ready? F10. Let's see what's wrong. Oh, just got the wrong return type up here. This should be a list. Like that. Okay, try one more time. F10. Okay, inside here. So look at split.
Yeah.
Look at what In fact, it's even telling you,
Ooh.
coders are telling you, this is the string. See that right there?
Yes.
That is the string. The string is 5, 7. The
Yeah.
result of it, though, look, see that? That means it's an array of size 2.
And it's a one-dimensional array of size 2.
Right, and it's got 2 entries. One is the string 5, and the other is the string 7 with a space in it. See it?
Yes.
Split turns a string into an array of strings.
Okay.
That's what split does. No worries. Okay, now what we need to do is this. Go through each element inside of there, and then we're going to come in here and we're going to say, hey, if int.try parse of item, comma, out int parse number, like that. We do one more
Why
thing.
am I making it an out int?
Because I need to get the value. If that's the case, then I'm going to go in here. Well, it's also the syntax for try parse. Try parse gives you back a result. So it returns true or false if it's successful. If it's successful, if this number is filled with a valid value.
Okay.
And now I'm going to come down here and say result.add and give in that parse number, like that. Okay?
Okay.
Cool? And now let me just clean this up a little bit. And now, if we step through it, let's watch it. So we got split string coming in here. We got a number. Now we're adding results to it, 5 to it, and we're adding 7 to it, and that's it. So if we look and hover over result, we've got 2 counts, 5 and 7. So we went from a string to a list.
Okay.
Got it?
Got it.
Give numbers. That's what it does. And now we got it to remove list. We're removing the 5 and the 7. Now what's in the square notes? We've got 2, also 5 and 7. Wait. Oh, I'm passing the wrong thing in here.
Oh.
That was a big mistake. How did you let me do that, Campbell? How did you just sit there and watch me make that mistake? Now we're passing in square notes, which is 2, 5, and 7.
Yes.
The square's got 2, 5, and 7. We can remove 5 and 7 from it because we know they have to be in the other 2 squares. So we're going to do this, and now we've got those 3. We converted that into 2, 5, and 7. Now we're just going to say for each member inside, first one is 5. Square notes, it currently has 2, 5, and 7. After we call remove, we're expecting to have only 2 and 7 in it. See it?
Yes.
Cool.
Okay.
Now we're going to come in again, and we've got just 2 in it now. And now our notes, which used to be 2, 5, and 7, after I execute this line of code, it's going to only be 2. That looks like it's working.
Works.
Okay? Cool. Cool. Oh, one thing we're not doing though is we're not returning solve result solved. We really need to find out if we've made any changes.
Oh.
Okay? So we need at some point to figure that out. And we're not doing that now, we'll have to do that later. But I think if we just run it, we may see that it's doing things it wasn't doing before. So right now, are we in the hard game?
Yes.
It's got a 4 all by itself in the upper right, it looks like to me.
4. Yeah, it does, because we haven't hit solve again once, yeah. And then now this 6 and that 2, and it can't solve anymore.
It's locked up.
Yes.
Okay, but we are further in
But-
this game than we got before.
Are we?
Uh-huh. I think so, or maybe not.
I don't think so.
Oh, you don't think so? Okay.
Maybe. Maybe some of the notes are different, but
Oh, you're right. We did kind of solve just the upper right corner. I thought we had already gotten to that point. Okay, so no, it looks like it's not working because look, when you hit solve, see the 178 up in the middle top?
yeah.
Those should all be. Wait, should those? Oh no, wait, that's the 3 rule.
Yeah, that's the 3x3 rule.
Do we have
we need
any
to
other
find an
options for the
instance
2
of
by
the
2
2 by
rule
2.
that's
Wait,
not being applied?
I'm gonna reload it, and then now we should look out for the 2 by 2 rule. We have 5, 7, and 1, 5,
Yeah,
7.
that
but
won't
no.
work. It's got to have only 2 in it. I think we need a middle game is what we need. What if you load the other game, the other hard game? See if there's anything in there.
Maybe. Oh, yeah, definitely not.
There's no 2x2s here either.
But there is a 4x4. Oh, wait, no, that's not. It's just 2 with 4. Okay. Wait, I want to see this again. Are there any...
So we found the 5-7. Where's the 5-7?
We have the 5-7 and the 1-5-7. But I don't think that's the one you're talking about.
Hit solve game once. Hit the solve button once. Now
Oh,
we have
5-7
two
and
5-7s. Oh, and look. I think this used to be 2-5-7.
Let's see. Wait, can we...
Yeah.
You're right.
All right, cool. Okay, so we do have confirmation now. It looks like the rule is working. It's just not enough.
Yeah.
That's a little frustrating to me. Can we try the other game and see how that works with the other game that you have? The control shift.
Oh, yeah. Control shift. Okay. No, we're not further.
Yeah, we just didn't get it. That's right. We already looked at this one. Okay. What about the main gun one? Is that the main one?
Yes, this is the
solve.
easy one. Solve. Wait.
And what's interesting about this is I almost feel like this, we should have counted how long it took to solve before. I almost bet this one solves faster. I almost think that this has got to happen here.
Well, let's see.
See if we get a feel for it. Can you hit the solve button? Looking for opportunities for the rule to be applied. Yeah, I don't see any opportunities now.
Dang it.
Okay, we gotta go to rule 3.
3x3. Yeah, I saw a couple of 3x3s.
Got a couple 1x5s, but they don't have any impact.
You're right. It is faster.
Oh, it takes fewer times, you think?
100%.
How do you know that?
Because the last numbers were not 5 and 4 before. It was, I almost feel like it got a different answer.
All right, let's try that. Let's see if we can verify that, because I'd like to visually see that. Let's go take our call to our solver. Let's go take that. This is right here. Let's get this code. Let's extract this method. Apply solvers.
Oops. Caps lock.
Like that. And
I feel like there should be a way, if you have something selected, to like hit caps lock and then for that to be turned to all capitals.
oh, that's kind of cool. Yeah, I like that.
Or if you paste something in with caps lock in.
So I'm gonna comment this out and let's run it and watch it and see what the last numbers are. And count how many times you have to hit solve to solve
Alright. Easy one. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, look, it's a different answer.
And then and one more to get you 11. So 11 hits to do it. All right, let's go back and add ours and see if we get it any faster
Wait.
than 11. Let's go back and comment the
I
code.
do think it's a different answer. But no, there can only be one answer.
You told me to wait?
No, you can go.
Okay, so it was 11?
Yes, it was 11.
Good job noticing that. That's super cool. All right, uncomment the code, run it one more time. We're looking for it to beat 11.
1, 2, 3, 4, 5, 6, 7, 8. Okay?
Okay, that's good news.
That's pretty good.
That is good news.
But also, wait, look, so it was, wait, can I have this for a second? It was
Yeah.
this 4 and this 9 that were last. But this time is, what is it? I think it was like.
All right, that is actually
Yeah,
really good
this
news.
4 and this 5.
Yeah, that's really good news. So we know that solver now appears to be working. One other thing, wait, before you close it down, load the game again, solve it almost to the end, then enter a wrong number in there, just to prove that our conflict highlighting is still working.
Okay.
All right, throw that number in here. Sweet. Nice. Okay. That was like a brain breaker, I think, to get that in. Whew.
The 3x3.
3 by 3.
Gonna be
Let's figure that out. Okay, back to my machine. What's our time? It's 40 minutes.
40 minutes.
Okay, 40 minutes to go. So now look at the 3 by 3. So this one's working. That's really cool. We can get rid of these two, I think. 3 by 3 rule. This is trickier.
Much trickier.
Basically,
Because the
what we
subsets.
need is only 40 minutes left in the show. That's right.
We
40
need to
minutes
pay
left,
attention to
Pudding.
the subsets as
What,
well.
what'd you say, Campbell?
For the 3x3 rule, we have to pay attention to the subsets.
Right. I'm looking for 3 numbers that are shared in 3 squares.
That are either in the same block, the same row, or the same column.
Yeah.
It might be actually more similar to the 2x2 rule than most things.
Well, I'm not entirely sure about that. I can't have, I'm pretty sure I cannot have any other numbers in there. Is that true? This rule I'm actually not so confident about anymore on this. I know if it's this rule is absolutely true. If I have 1, 2, 3, and only these numbers here, if I have a subset and not anything else, right, then I can also apply the rule. What I'm not sure about, Campbell, is what happens if I have like a 4, right? If the 1 and 2 are nowhere else, then this can't, in none of these other squares right here,
Yes, then
Then
that can't be it.
then the 4 can't be there. But I'm not sure how to do the logic for that rule. But I think I can figure out the logic for this part, where it checks for this or subset, is what I think I can do. And I guess we'll do that as the rule and see if we can make that work. That's kind of what I'm feeling. I don't know, what do you think? Also, you can, this is your show too. We can do it whatever you want. So, you want to do this? Want to take a break? Mind blowing?
Here's the thing. I think I do want to do that. But wait, I was just checking something. What happens if I solve it all the way? And can it still solve? Yeah. Okay. I think that the 3x3 rule, we might not be able to finish it by the end of the show. Might. But I think we can.
Alright, the tricky part with the 3x3 rule is I would use a different iteration technique than we did with the 2x2.
Let's try for now just the slide number 14. And then I think if we can finish that by the end of the time, we can maybe start strategizing.
Oh, I was going to put these both in the same. I think I can do them both, but I'm not. Let's at the very least we'll build an iterator first. We'll build an iterator that iterates through, and we'll create that solver. Oh wait, one other thing we need to do. Let's go back to our solver 2x2. Let's make a little bit of refactoring before we get out of here. I want to do this. Call this new notes, like this. Then I want to say, hey, if new notes is not equal to square notes, then we're going to assign them, but we're also going to return solve result dot square solve. Okay?
Okay.
Otherwise, we're going to return solve result dot none.
Wait, what? You just did a SR and then it worked.
Oh, that was, so I did SR, so I put the capital letters in, and IntelliSense does this. That's Visual Studio.
Ah, that's cool.
Yeah, it is. It's cool. Alright, and then I'm going to hit the code rush key, convert this to a function. Notice it's a void. See right there?
Yes.
When I hit convert to function, it returns a solve result.
Ooh.
Then tap the next reference down here, and what I want to do is I'm going to need to get some sort of solve result up here. Like I'll do this. I'll say result, and I'll set that equal to solve result dot none. And then right here, I'm going to check to say, I'll say, hey, if that is equal solve result dot square solve, then we're going to set result equal to that. And then we're going to return result at the end. So now at least we're going to know. Oops, result is what I want to send back out. Now we'll know if it works or not. Now, what I want to do, I've got a couple methods in here that are useful. I've got one called node count,
Yeah.
right?
Uh-huh.
But I'm in my solver 2x2. It descends from base group solver. Gosh, it would be great if base group solver gave these really useful methods to everyone and they could call them. Those are our dogs in the background. What'd you say?
It can. Because the interface.
What'd you say?
Because of the interface.
Yeah. I'm going to use pull get numbers up. Pull it up. And we're going to put it up to base group solver. Like that. So we just moved it up to it.
Wait, what?
We just took that method and pulled it up to base group solver.
Okay.
So look inside base group solver to see it, and you see it's now in here. Got some issues because we just need to use system collections generic, but now we used it, and now it's up here. So base group solver is getting a little bit more useful. Okay. Let's also get the node count. That was super useful too. Pull that number up. Okay. I'll put the abstract method at the top. I like to keep that up at the top. Okay? So now we've got this cool base group solver. Now I want to create a new descendant of this. This is going to be my solver 3x3. And it's going to descend from, what's it descend from, Camel?
It will descend from the base group solver, right?
That's it, exactly. So we descend from it, we get the red squiggly line, so we want to choose abstract, implement abstract class. That's going to add the methods we need to override. There they are right there. Let's go ahead and move this to its own file. Okay. The other thing I want to do with my solver 3x3 for the 3x3 role is I want to go find my 2x2, tap to next reference on this guy, Campbell. So I want to find that line of code, duplicate it, and replace it with that. So now I've added my 3x3 solver to it. And that's all I need to do. It's now going to apply the 2x2, then it's going to apply the 3x3. It's going to do all of that.
Really?
Yeah, because it's in a list. See, we've got this for each here. Every solver I add, it's going to go in and throw the solver at every one of these.
Oh, but it's not done yet, right?
Nope, not done yet.
Yeah, okay.
No, not done yet. I need to implement the solver 3x3 because I haven't done that yet. So there it is right there. Well, the first thing I need to do is I need to look at I need to start looking at combinations. I think what I need to do is find all the combinations. So here's the deal. Let's switch back to my machine. So if you give me 3 squares, Campbell, and I only have to look at 3 squares, let me duplicate the slide here a second. Delete everything that's not those 3. If you give me only 3 squares to look at, I think I can figure it out with those 3. I can look to see, do they all have only those 3 nums or a subset? I can do it. I can do it, I can do it, I can do it. I can totally do it. But the question is, how do we find every combination of 3 notes available to compare them.
I think that once we find one combination, we have to save it in a list or in a dictionary, as that we have gone through that combination. And then I think we do that, we just brute force it.
All right, let's see what we can do. Here's what I'm going to do. I'm going to create, I'm going to have 3 for loops is what I'm going to do. I'm going to have 3 variables. F is equal to first, S is equal to second, and T is equal to third, like that. And so we're going to say my first for loop like this, and that's going to have the letter F in it. And that's going to go, yeah, it's just going to go through the group link like that. Then I'm going to have S as the next one. And I'm just going to say, hey, look, if S is equal to F, then continue. But if not, then we're going to keep going. Okay? And then inside here, I'm going to have one more for loop. That's going to be my T for the third. And so what I'm doing is I'm iterating through every single 0 through 8, 0 through 8, and then 0 through 8 to find 3 pieces. I'm checking to see, hey, is S equal to F? If it is, I don't care. I'm not going to compare the same square against itself.
Okay.
Okay? Then down here, I'm going to say, hey, if T is equal to F, or if T is equal to S, in other words, if the third one is equal to the first, or the third one is equal to the second, then I'm going to continue. But if not, then I'm down to here. And now I've got magic. Magic. I've got 3 squares. You see what I'm getting at right there?
Yes.
And let me spell squares correctly because that's kind of important. So let's rename these so they all have good names. You cool with that?
Yep.
Third. Whoops. First. Second. These are indices. They're just numbers right now. I'll get rid of that comment. Okay? So now I've got 3 squares. And they look like this. It's of type I Sudoku square. First square is equal to group of first. Second square is equal to group of second. And third square is equal to group of third. Okay?
Okay.
So I've got 3 squares. I'm freaking excited at this point. Now that I have those 3 squares, I need to figure out, you know, what are the numbers that are inside all of those, is what I need to do. And I think I'm looking for a count that's either 2 or 3 in all of these. I think, as I understand the rule. So I'm going to do this. Let's check each one of these. So we want to say, hey, let's do another thing. Let's come in here and say, let's say first notes, first note numbers is equal to get numbers of first square dot notes. We'll do the same thing with the second. That's going to be the second for there, and then we'll do the same thing for the third. We need to move these down because the others have to go. So now we've got a list of numbers for each of these. So we'll say, hey, look, if first note numbers dot link dot count rather, the count, there it is right there. If count is less than 2, or the count is greater than 3, then I can't do anything. Pretty sure I can't do anything. So we'll say continue.
Okay.
Oops, and that should be this right there. Like that. So I need that, and I want to duplicate that twice. Like that. And put these in the right places as well. Okay?
Okay.
So we're now checking to see all these. Now because of this, I kind of want to get out as quickly as I can. So I'm going to do this first check up here. Then after I get the second square, I'm going to do a check on it and get out because I don't want to do extra work. And then I'm going to come down here and do this. So at this point, now we've got super magic right here. Super magic, right? This means we have 3 squares. Squares that all contain 2 or 3 notes. You agree with me?
Yeah.
Okay, cool. Now what I want to do is I just want to set a breakpoint right here. I'm just going to set a set of empty braces here so I can just break on it. That lets me set a breakpoint there. I'm going to return solve result.none for now, just so that this compiles. We're going to run and see if we get to this breakpoint. Oops. Right there, I want to put that. Okay, cool. Let's run it. Okay. New game. We're at the hard game. Let's solve. Ha! Look at this. Let's look at what our data looks like. First square, first node numbers, it's got 2, 4, and 7. Second node numbers, it's got 1, 4, and 7. Third node numbers, it's got 7, 8, and 9.
Yes.
Okay, but at least it qualifies in what we want it to be so far. Next, I think what we want to do is we want to go through every list that we've got and add the numbers to another list if they exist. So we're going to say all numbers found. So we're going to create a new list event called all numbers found. It's got nothing in it right now, okay? But then what I'm going to do is I'm going to do this. I'm going to do for each, let's call this number. In first node numbers, do if all numbers found, if it doesn't contain it, the number, whoops, hold on, it doesn't contain the number, then we're going to say all numbers found, add the number. Okay? We're going to do that for the first node numbers. And I think what we could do is we could create a function that does this. And we're going to call this add numbers.
You mean a method?
To a method, I'm sorry. I say function?
Yeah.
Let me reorder the parameters here. Have you ever seen reorder parameters? Isn't that cool?
That's so cool.
All right, all numbers found comes first, and then first node numbers mistakes.
Wait, so it's just the coder's key?
Yes,
and then
coder's feature, yeah. And
the
then
left and right arrows?
Yeah, choose the reorder parameters, and then left or right arrows, and then hit enter. Yeah, sweet. All right, so we're going to duplicate this, second and third. Then, let's go look at that. Let's step through these codes and see what we have. Wait, what happened? We lost something here.
Uh-oh.
I'm sitting on do here a second. What's my problem? Is it okay or not? I'm going to hit F10. See what happens. What's my error? My return's in the wrong place, it looks like. Okay. Did I get an extra return in there? I think there's an extra curly brace got in there too. Okay, that looks better. Okay, so now, where are we? I think we're about here. That's where I think we are. So we'll create a new list. Now watch what happens. First node numbers, whoa! How did first node numbers get null? All right, let's come back up here. Do this again. Okay, so now we're here. F10, all numbers found. Now all numbers found so far has got 3 numbers in it. 2, 4,
Yes.
and 7. Again, all numbers found. Now there's another one. At this point, we're done. We need all numbers found to only be 3. You can only find 3 numbers in those 3 squares.
Okay.
Okay? So, but basically the idea is this, is, well, okay, if all numbers found dot count is greater than 3, then we're done. We didn't find it. Okay? We're going to continue and we're going to keep going and looking. But if not, I'm going to set breakpoint here. We're going to get to super duper magic in a second. We get to that breakpoint. Oh, we don't get to that breakpoint. No, no. Try the easy game. See if we get to that breakpoint in the easy game. Are we really going to have to do a brute force? Okay, we got it on the easy game. All right, so what do we got here? We got all
Wait,
numbers.
I think we could have gotten it on the hard game. We just didn't hit solve.
Oh, okay. Let's
try it again. I think.
Okay, good. Just stop the program and restart it on the hard game. You're going to have to stop it and restart it because the breakpoint's here and the fastest way is to hit Shift F5 is the way to stop the program. You can't activate the program like you're trying to do because you're at a breakpoint.
Shift.
File says, hey Mark and Campbell. Mark, do you have any videos teaching about MVVM or any recommendations for where to learn the topic for C#? I don't really. I would, if you have a plural site subscription, I'd go out there, look at that. That's kind of where I'm at.
We got to the break point on the hard game.
Oh, we did get to the break point on the hard. So sorry, unfortunately, Val, I don't have a great recommendation for you on that. I don't, but if I was searching for it, I would add words like quick or quick tutorial, introduction tutorial, that sort of thing. Because I like to get my information fast and furious, very quickly, but not a lot of information, just the essence. I have found though that there are great tutorial content online that you can read if you don't mind reading. There's stuff online with regards to that. I don't have any links, but Google it. That's what I'd be doing right there.
Okay.
We're almost done with the show and we're rushing through the code file, so I'm not going to look at it now. But before the end of the show, I'll try to get out there and take a look and see if I get any recommendations. We're at a break point, Campbell.
Yes.
We're at a break point. What are our numbers found? What do we got? 1, 7, and 8. Sweet. That means we know that 1, 7, and 8 are only in these spots of these 3 squares, which are indexed by first, which is 0, second is 1, and third is 2. So the first 3 squares have only those 3 pieces inside.
Yes.
So now what we want to do is we want to say remove. Do we have a remove all numbers? Did we create something in here?
I thought that was for something else.
In base group solver, get numbers is what we added.
I don't
Okay.
think that's it.
Solver 2, remove notes from.
Remove notes from.
Well, we need something along these lines. Remove notes from, we need to kind of move it up, I think, because we want to use it in both places, I think. But we need to go through the group, is what we need to do. We need to check to see if all numbers found. No. We need to see if I equals first, or if I equals second, or if I equals third, like that, then we continue. But then, if we get down here, now we're actually removing. Now we can actually solve. We can actually remove. Which means, we need to see if we can remove it or not, see if it has it. We need to get remove notes from. So I'm going to stop the program. I'm going to go find remove notes from. And let's go with that key instead. Really, jump symbol, it's not grabbing remove notes from. What I'm going to do, I'm going to take that and pull it up. Just going to move it up to basic group solver. And we just moved it up there. We can go check the basic group solver. Should have remove notes from. Whoops, sorry, that's solver 3x3. There's basic group solver. There's the remove notes from, Campbell. Let's make it public so you can see it in both places. And now we've got remove notes from is working. We need to pass in the notes as a string. So what we're going to do here is we're going to say string.join, pass in the commas. It's going to be comma separated. And we're going to then pass in all numbers found. Like that. And we're going to call removes the notes from. If it equals square solved, then we're saying result is equal to square solved. Then we're going to return result right there. And we're going to have to declare it up at the top. We're going to say result is equal to .none. And I think there's a shot this is going to work. We get to this breakpoint, we've actually eliminated something from a group. Okay? So we've got a breakpoint here and there. Let's run it. Get me in there, Campbell.
Okay.
Give me to a breakpoint. So loading the game, hitting solve. Nothing yet, nothing yet.
Yeah.
Ah, we got something. Sweet. So now what do we have? The numbers found, I think the same as before, I bet, right? Oh no, 178.
Is the same as before?
Oh, it's 178? I thought, okay.
Yeah,
And-
wait, what did you think it was? I could be wrong.
No, 0, 1, and 2. That's what I was remembering. So it's an
Yeah.
index 0, 1, and 2. It's got 1, 7, and 8 in it. So so we're now inside here, and that's good news. We're gonna hit F10. Now we're gonna go through everything in the group. Oh, no, the first one, the second one, and the third one, right? I is equal to 1, right? 0, 1, and 2. So now we can only look at indexes 4 through 8, which are the remaining squares. Can you visualize that, or do we need to see that?
No, I think I can visualize.
It's over here. It's as if we had something like, let me duplicate the slide here and add a 3 here. Right? It's 1, 2, 3, and this one's 1, 2, 3. And then the next one over here is also 1, 2, 3. It's like that. So we can only now look at 4, or, well, it's actually index 3 through 8, not 4 through 8. So we're looking at 4, these squares over here. Do they have a 1, 2, or 3 in them? If they do, we get to take it out. That's what we're talking about.
Okay.
Okay? Pudding says 1, 2, 3, 1, 2, 3, testing 1, 2, 3. Okay, now here's the real key. We're really looking for the next one to get through. Sweet. Now we're checking to see if can we remove anything. That lunch is delicious. I'm getting hungry. That's what I hope, Campbell. All right, switch back over to your machine. Sorry about that, guys. Group of I. Can we highlight that whole thing and then hover over it? Group of I is nope, it's not. I thought I could select the whole thing and then hover over to selection. Nope, it's not doing that for me. If we step into it, we'll be able to see it. Sudoku Square here. It's got it's got a value property down near the bottom.
I think we should cook for her.
It's
instead.
empty, so there's nothing there. So let's set a breakpoint down here. Sweet, we got a breakpoint. Ah, look at that. Well, 178, we're moving from what's in the square. Let's do this. Let's right-click this and say Add Watch. I don't know if you've seen the watch window yet. You come down here and type in value. Oh, sorry, not value. Notes is what I wanted to look at. Notes. Oh, cool. Look at this. See? 1, 3, 4, 5, and 8. And we can remove 1, 7, and 8. See it? This is the square. It's already got those big lot of notes. We're going to be able to take out the 1 and the 8 from this. So we step through this.
Well, that's good.
And we get out of here and check it out. We're still in our solver 3x3. That means we just solved. The solver 3x3 just helped us. Now I'm going to clear the breakpoints and let's watch it. See if we get any bit closer. Good, Campbell. See what we get with the solve. Can we get any closer with
Oops,
solve?
wrong one. Ah. I was hitting the wrong button.
No. Still stuck. Let's
I
go
don't
back
know
to our
why
easy.
the solver 2x2 isn't working here.
Well, it's not working because there's nothing else to take away from the left or right. All the other ones are filled. The solver doesn't change the 2 we found. It changes every other one in the row. And since every other one has a value, there's nothing we can do. Try the easy game and see if the easy game solves in, what was it, 8 hits?
Yes, it
Or
was
if it
8.
goes in fewer.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It had the exact same outcome as it did before.
Yeah, it seems like we completely taking a step backwards.
Yeah, it's like, wait, did we accidentally undo the 2x2 rule?
I don't think so. Because that's just coming from the list. The fact that 3x3 was going when we're stepping through that indicates a 2x2 should have been working as well.
Well, it appears that it wasn't at all. Or the effects of the 3x3 were trying to kick in when the 2x2 should have been trying to kick in. And it undid.
Yeah, I don't know. I don't quite see what's happening. Let's see if I can if we can run it and figure it out. So load game, solve 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Yep, it's the same outcome as before.
Okay,
When
let's
we didn't have the 2x2.
take out our 3x3.
Or at least comment it out.
Not sure what's going backwards. That doesn't make sense to me, but we'll see. Load game.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
11. It's not working either.
Huh.
I think there's another potential problem. I'm thinking it might not be here or here. I'm thinking it may be here. This is the first time I think we've tried calling refresh all notes afterwards. I'm wondering if refresh all notes is having it go backwards. Let's try reply solver here, like this, and just see what happens. I don't know if it's gonna work or not, but let's try it. Load game. 1, 2, 3, 4, 5, 6, 7.
Oh, wait a minute.
Yeah,
1,
so
2, 3, 4, 5, 6, 7. Yeah, okay.
so we actually got it in fewer steps.
1, but still, that's fewer steps.
Yeah.
I wonder if now.
It'd be nice to see that rule, where it is, where that rule is being applied. We can do it by setting a breakpoint and then examining it. Let's do
So
that.
4.
Let's do a breakpoint.
We can get 4 steps in the hard game.
There are points in hard or proper Sudoku where you have to guess and branch out from the one that doesn't lead to an erroneous answer. We're going to do that, I think, next Friday. Bob. We're going to do that. We're going to do recursion to do that's going to be our final step. Square solved is true. What I want to do is go to the 3x3 solver and set a breakpoint here. And now let's run it.
There?
And that'll tell us what the values are. Go ahead, hit solve on that, and then we'll get the breakpoint.
Oh,
Nice, already here.
Immediately.
So we need all numbers found is 1, 2, and 3. The group of I is what's I? I is 6. So group of 6 got value. No, it was value. It was the notes. Is what we want to get to. Sorry, notes. It just got 9 left in it, and it is in it's in 6, 0. So let's double check, make sure I'm right on that. 6, 0. So 0, 1, 2, 3, 4, 5, 6. Yeah. So we're in this space here. The all numbers found. Let's go back and watch, keep our eyes over in this space. So let's load the game again. Load, whichever one you're doing, this one? All right, hit solve and keep our eyes in that bottom left column over there. So we've got a...
1, 3, 1, 3, 5.
I like to call it Sudoku because ducks. Yeah.
Because ducks.
Sudoku. Let's put the
Oh wait,
back in there
we
again.
have kind of a subset. We have 2, 8, 2, 7, 8. No, not really.
Wait, that's totally it. Oh, except for the 7 won't qualify because it's got
Yeah, it's only
1 and we don't need it. That's not an
That's
interesting
the
thing
thing.
to us. Let's set a breakpoint again in there. Let's put the breakpoint back in there. Right there. And let's get it again. Alright, load game. Solve. Okay, so solve 1. This is it's group 6 again, which we said was a 9. What's its value? Right? It's I is 6. All numbers found is 1, 2, and 3. Let's bring our watch window up here. It's going to be much easier to see this. We'll bring the watch window up. And let's put in group of I. So we'll say add watch. And we're going to say dot notes. Shoot. Like that. So we can see it's got a 9 in it. All numbers found. Let's add that to the watch. And it's just count 3, but I think I can do this. I can do a string dot join call on it, and then pass in. So I'm just. I
Wait,
can
what are
actually
you
do this.
working in right now?
What am I typing in now?
Yeah, what are you working in?
I'm just putting some entries in the watch window so that I can see what the values are as we step through the code.
Oh.
So I've got a 9. The 9 is now left. We need to know what column it's in and row it's in. We don't really know that from here because it's kind of passed in as just this group. But we could get out to the end here like this, get to the end, come back out, and where are we? So we can see we were looking at column 0. So in column 0, there's an entry with that had more than 9, and we removed a 1, 2, or a 3 from it in column 0. So let's run it again. Let's set the breakpoint here a second. I mean, stop the app and run it again. Let's look at column 0. Right here. We hit solve. The solve the first time gets in. So it just takes it out the very first time. Let's maybe find the second time. I mean, the second time's going to be more interesting. And here's this. No, this is still the same column, the first one. Clear that. We get the first solution. Hold on, I want to set a breakpoint. Now hit solve. Okay, cool. So now we are looking at 1, 4, 9. Okay, so we're looking for 3 squares that have 1, 4, and 9 in them. And let's get out of here. And now we're looking at block row 0, column 2. So let's look at that. Block row 0 is here, column 2 is this one. We're in this space here. Okay? So what we're going to do is we're going to load the game again, hit solve, and then get our eyes up in that upper right. What was it, 1, 4, and 7?
Yeah, I think it was 1, 4, and 7. Or no, I think it was 2, 4, and 7.
2, 4, 7, 2, 4,
2, 4, 7
7,
would make sense.
2, 4, 7.
I think it was 2, 4, 7. Here, wait, can I?
We must get rid of the 8. I bet the 8 goes away in
Yes,
one of the earlier moves.
I think, yeah, the 8 goes away, and then we have 2, 4, 7, 2, 4, 7, and then I think we either have 2, 4 here or 2, 4 here.
Wait, yeah, but look what's going to happen. The 2, 4, before you hit solve, watch. If the 8 gets removed...
Wait, the 4 is going to get removed in all of these because
yes, the 2 and the 4 and the 7, those will all go away here. Hit solve and see if that happens. So eyes in that upper right.
Yeah, not the 4 here though.
2, 7, and 8, it was the 4 that got played, I think. The 4 is... How do we remove the 4 from that? 2, 7,
Here.
and 8.
The
Oh,
4
and
was
that...
played here.
Okay, I see. Okay, let's go back, load the game, watch it one more time in that space. Solve once. The 4, I see. The 4 goes down
Yeah.
here. Removing it from here, that now satisfies the rule. We're going to remove the 2, the 7, and the 8 from over here. So 7 and 8 will go away there. The 2s will go away here. And the 8 will go away there.
Okay. Do you
So
want to
let's
see?
watch
Wait.
that.
Can I?
Wait,
try
let's watch it.
Okay. Wait. 1. Yeah.
Yeah. All right, cool. So that's cool. Not bad. We implemented 2 logical rules. They're a little mind-blowing.
I
Let's go
think
see
a
if I
bit more than a little mind-blowing.
can... Wait, what'd you say?
It was a bit more than just a little bit mind-blowing.
Yeah, a little bit more. You want to go back to simpler days?
No, I like it. Once I understand it, it's very fun. But like before that, it's kind of really just confusing.
All right, I'm already a huge fan of this answer right here. Vile, take a look at this on Stack Overflow. I'm going to put this up in the chat room and switch over here. I like this answer a lot. It's got 161 upvotes right here. It's got a nice collection of tutorials on MVVM right here. I feel like you're not going to go wrong there. Okay. I also like, breaking this down here, asking 2 questions here. Something you know previous, and then if you do have previous experience, you'll just probably go faster. So take a look at that file, no worries. Kemal, you want to check in the code?
Sure.
All right, Kemal's going to check in the code. I'm going to get a raid going. I'll send you out to somebody else out here, out on the interweb,
We added
in the lab servers team.
2 rules.
Yeah, you're welcome, Pudding. Thanks for hanging out with us today. We'll send you over to Lana Lex. She's doing game development.
By 2.
Get that started. Cable's going to check that in. We'll see you next week on Kids Code on Friday and Saturday. And then I'm doing a Code Rush show. You can catch me writing code in C# and TypeScript for the other 4 days of the week. Tuesday, Wednesday, Thursday. 3 days of the week. I can count. Have a great day, kids. All right, sending you over to Lana Lex.
Have a great day.
Campbell's checking that in.
Goodbye.
Goodbye, kids.